Hi everyone, my name is Matan Benoit. I'm from Intel, and I'll present the work Compressing Pre-trained Language Models by Matrix Decomposition. This is a joint work with Yoav Goldberg from Bar-Ilan University. So, pre-trained language models contain important logistic information and rich state-of-the-art results because of that, but they also come with a large computation and memory requirements because of their large parameter count. These large models may act as showstoppers in many applications. So our goal in this work is to compress these models, but we would like to do so while still maintaining the information contained within them. In this work, we are focused on task-specific model compression. So in practice, we would like to maintain the same behavior after the compression. What do I mean by maintaining the same behavior? I mean that we would like the compressed model to have the same predictions as the original model. So how do we achieve this? We decompose each matrix into two smaller ones using singular value decomposition. This will give us a reconstructed matrix, which will be the best approximation we can get for the original matrix for the desired dimension that we want. However, what we really want is the best approximation we can get for the outputs of the original matrix. For this, we further train the matrices on task-specific data to minimize the R2 loss over the outputs. In this work, we are focused on fine-tune model compression. So we take the task data, we fine-tuned a pre-trained language model, we decompose the fine-tuned model, and then we further train using the same task data, the decomposed model, to get a fine-tuned decomposed model. So how does the decomposition differ from previous approaches for pre-trained language model compression? Previous approaches suggested to remove certain layers of the model. Here we keep all the layers, but we decompose them. Although layer removal does achieve faster inference speeds, the main problem of it is that it's very hard to control the compression accuracy trade-off. For example, if we only wanted to remove a small number of parameters from the model, we had to remove an entire layer to do so. Additionally, many of the approaches that remove layers require longer training times. Many of them require redoing the pre-training stage, and all of them reach higher reduction in accuracy in most tasks. Layer decomposition, in comparison, can easily control the compression accuracy trade-off by simply deciding which dimensions to use for the smaller matrices. It only requires the same task data, it only requires the same iterations as fine-tuning, and it achieves less than 0.5% accuracy loss on most tasks. So our solution here is composed of two stages. In the first stage, each matrix is decomposed to two smaller ones using SVD. And in the second stage, information from the uncompressed model is distilled into the compressed model. So how do we train the decomposed model? We use a feature distillation training regime in which the teacher model is the uncompressed model and the student model is the decomposed model. And the distillation loss function is an L2 loss function between the representations given by the student and teacher models on every layer of both models. Additionally, we use a cross-entropy loss function for the decomposed model. So our loss function is composed of two components, a cross-entropy loss function and a distillation loss function. In this experiment, we tested 3 different models on 8 tasks from the GLUE benchmark data. In red, we see a BERT-based uncompressed model. In blue, we see a decomposed BERT model. And in gray, we see a state-of-the-art approach that removed half the layers from BERT-based model. We can see here that a decomposed BERT model outperforms a 6-layered BERT model in most tasks. And in most tasks, we can also see that a decomposed BERT model achieves minimal loss in accuracy compared to the uncompressed BERT model. In this experiment, we tested the effect of feature distillation and the effect of the decomposition. We conducted this experiment on 3 tasks from the glue benchmark data. Left bars show models initialized using an SVD decomposition. Right bars show models initialized randomly. Red bars show models trained with a teacher, and blue bars show models trained without a teacher. We can see that decomposed models significantly outperform randomized models, whether we use a teacher for training or not. We can also see that models trained with a teacher significantly outperform models that were trained without a teacher. Additionally, the best results are when using both initialization with the decomposition and using a teacher for training. So we can learn from this that both things complement each other. In this experiment, we tested the work log time in milliseconds it takes for different models to process batches of different sizes. We conducted this experiment in a CPU environment and in a GPU environment. In red, we see a BERT-based uncompressed model. In blue, we see a decomposed BERT model. And in gray, we see a 6-layer BERT model. We can see here that a decomposed BERT model is about 1.4 faster than their uncompressed counterparts for batches larger than 1 when running on a GPU, and around 1.3 faster when running on a CPU. So to conclude, pre-trained language models contain important linguistic information and reach state-of-the-art results because of that. When compressing them, we should try to maintain the information within them. Here we presented a matrix decomposition compression approach, which maintains the information within them. It can easily control the compression accuracy trade-off. It only requires the same training data. It only requires the same iterations as fine-tuning, and it reaches less than 0.5% accuracy loss on most tasks. And that's it. Thank you.